Good morning, everybody. Welcome to Boston. Welcome to MIT. I'm Curtis Smith. I'm one of the professors here at the Massachusetts Institute of Technology in the Nuclear Science and Engineering Department. So as a university, we welcome you all. You'll be joined, I think, by another large group of folks at the 9:30 point. But just wanted to thank you for coming out for the PRA introduction. We have an action-packed week here. We'll talk about a lot of applications, some lessons learned, some of the great things that risk and operational kinds of insights to PRA can bring to us when we're operating our facilities. But of course, this morning what we're going to do is go through just a very high-level introduction of what is PRA. Talk about some of the tools, methods, and applications. And you'll, of course, see a lot more of this during the week, where we'll focus maybe less on the technology and the math and the science behind PRA, but more on what it does for us as an industry. If you have any questions in this break or in this session or during the week, please raise your hand. We've built a lot of time in for dialogue and discussions and workshops and engagement with the speakers all through the week. So definitely try to participate that way. So there are seats down in front if you're looking for a seat. So let's go ahead and get started. So what we want to talk about this morning, we'll see kind of a formal definition of what is PRA, how probability, of course, and predictions underlie that approach. We'll talk about two specific models of entries, fault trees, and then what supports that reliability analysis. And then we'll put all of this together in a package. Of course, we're not going to see right now how we use PRA. We're not going to see how PRA is wrapped up in our risk-informed licensing. That's really the topic for the next 4 days, though. So, one of the key concepts here is the idea of risk. And risk really just means some kind of performance shortfall you have. If you're running a nuclear power plant, you have different kinds of risks, of course. You have worker risks, you have potential risks to the public health and safety, you have economic risks, electricity generation risks, and so on. And so we have to really specialize what we mean when we say risk. And we'll talk about a couple of different approaches, starting here with one of my favorite cartoons, Calvin and Hobbes, from back in the day. Some of you might remember these. So I think it's the family driving in the car, asking a risk-related question. How do they know the load limits on bridges? That's a good question. You would like to know your safety margin, right, in your back seat of that station wagon. In this case, it's 10 tons, whatever that is. But a solution to the problem. As an engineer, this is a great solution, right? You take bigger and bigger trucks until the bridge breaks, and then they weigh the last truck and rebuild the bridge. Now, of course, there's a lot of problems with that. Reproducibility of the bridge, of course. If you've been around a manufacturing or construction process, you know that's not a perfect process. It would be a little costly to do this, but nonetheless, that's an approach. Gather data, find your safety limits, move on. And of course, if you don't know the answer, you make it up, right? But we'll learn this week that we're going to bring in a science to what is risk, to have these models that essentially provide a knowledge base for how our facilities are going to operate in the future. Now, there's a couple ways to do risk analysis. You can look at actuarial analysis. Insurance companies, of course, do this, where you have a lot of data related to, again, you have to define your risk. So if it's mortality, you might have a population of death rates and accident kind of causes. And then you write insurance policies against that. But to do that, you have to have that database. You have to have a way to kind of evaluating the data that's coming to you. Now, fortunately, in the nuclear industry, we don't really have this kind of data. You know, we don't have 1 million core melts that we can then specialize. We don't have 1 million deviations from, 100% power. Instead, we have different approaches. And historically, we started with things such as design basis accidents, maximum credible accidents, and those still play a role. But this week, we're going to see how we've evolved our thinking and risk to PRA. And each one of these, of course, have pros and cons, have limitations, and so on. For example, the maximum credible accident, that's an easy concept, but in practice, it's actually a difficult thing to do, to pin down, what's maximum, what's credible. Those are two simple but difficult words. The accident that a lecturer typically would focus on here is, imagine you're providing kind of security for the Super Bowl, and you're looking at worst case scenarios, and you say, okay, well, what if somebody flies, a 747 into the Super Bowl? Is that a worst case? Is that even credible? And you can't say that's worst case. What if two planes collide over the Super Bowl? And you start on that kind of a slippery slope. And that's really one of the motivations for PRA, where we try to bring in realistic scenarios and credibility into the picture rather than just purely speculation. So we have this nice tool, this way to capture knowledge related to our facility. Probabilistic Risk Assessment. And yes, it's going to give us metrics such as core damage frequency. It'll tell us things about the probabilities that our humans fail, our components fail, our systems fail. But it's really the insights, the scenarios, the potential upset conditions, and how likely they are compared to each other. That's the strength of this kind of a risk assessment. Now, if we're talking about typical PRAs for nuclear power plants, the main metric that we use is CDF. You've probably heard of that before, core damage frequency. It's a metric on kind of a surrogate, if you will, for public health and safety. Melting the core doesn't necessarily mean you're going to impact the public, because we have so many layers of defense in our facilities where it takes a lot of things to go wrong, of course, from radionuclides leaving the core to people ingesting them. But nonetheless, it's a concept that we want to get our hands around. And so we have to define the metric. Could be CDF. Again, it could be things like financial losses, electrical production, but other things. And what we want to do then is have a formal, scientific-based way to kind of look ahead of potentialities. And I like this quote from Mark Twain. It's not what you don't know that kills you. It's what you know for sure that ain't true that's going to get you in trouble. And one of the things that PRA does for us then provides a sounding board, a dialogue, where rather than just speculation or opinion, we try to put some facts to the statements and to the insights that we're producing. Now, to do a PRA, of course, we have to have a cadre of knowledgeable people. We have PRA people, licensing people, systems analysts, plant people, and so on, because it is really a knowledge base. You don't just have a PRA person go off, come up with a number. That's not what we're talking about here. It's really an encapsulation of what do we know. Now, that knowledge is not perfect, just like any plant system component level knowledge is not perfect. It's, making predictions is hard, especially about the future. And what we want, though, is to have some scientific basis for the models that we want to use, because as we'll see this week, the decisions we're going to make using PRA as an input are very critical in terms of public health and safety, in terms of economics of our facilities. So the higher fidelity that we can have, the higher robustness in our decision-making, of course, the better off everybody is. So risk. You typically will hear the word risk in a formal setting talked about with this risk so-called triplet. What can go wrong? Meaning the accident scenarios that are postulated, how likely it is for things to happen, and then what will be the outcomes. As I mentioned, things like a core melt still has barriers to defense before we impact the public. And so we would have core damage as a metric. We might have other kinds of metrics, dose to the public, and so on. And then lastly, we have another question that we ask sometimes is, how well do we know what we think we know? The uncertainties are related to that because that could also impact the decisions we make. So pictorially, one of the fundamental concepts here is once we understand the risk picture, the target, the criteria, if you will, we want to have a science-based way to look at upset conditions. In other words, we know we're going to be starting from the left-hand box here. It says desired system operation. That's what you all do very well, 7/24/365. We're in that box a large fraction of the time, which is great. But what we're concerned about when we're looking at a risk assessment, and what we're concerned about this week, in a sense, is those deviations from normal operating conditions. What will push us into an undesired state? And eventually, of course, then we need to talk about the likelihoods of those. But starting from simple concepts, this idea of a scenario, and we will build then our tools and our models around that, of course. Now, to do an adequate job of the scenario identification and scenario modeling, we need to know the boundary conditions. That's where that knowledge base of the plant comes in, because it doesn't really make sense to make a scenario where your plant will not follow the evolution of that scenario. And by scenario here, I mean things like trip set points, pressures, temperatures, what is the RPS going to do, what are the operators going to do, and so on. Now, you might start to be concerned about, hey, there's a lot going on in my facility. How do we model everything? How do we model every step in the procedure? How do we model every evolution of temperatures and pressures? And we don't, of course, model everything. Nobody does in engineering. What we do try to capture are the important things. And where are the key things that we need to worry about? And ask, if this doesn't go right, is things going to get better or worse? And then if that's the tripping point, that's where the quantification starts to come in. But again, just think conceptually about scenarios. Think about a bad day at your facility, what that might look like, and a way to capture that at a high level. Eventually, though, we want to represent the middle and the right-hand side of this figure. We'll need then models that talk about the system does not compensate for that upset condition. We have safety systems and other systems. We have humans in our facilities to help us. We want to avoid, though, moving from left to right as best we can. Nonetheless, the scenario model will capture that evolution. And it may be that probabilities get smaller and smaller as we move from left to right. That's okay. That will be built into our risk model, of course. And then ultimately, we will say something about the consequences, depending on the risk metric. If it's core damage frequency, we just stop at core damage frequency. We don't really talk about the consequences because CDF is a surrogate for other kinds of consequences that we'll talk about in a second. But nonetheless, we could kind of go clear to fatalities, cancers, and whatnot if we wanted to. It's up to us to decide that modeling standpoint. So slide 10, I stole this figure from the NASA PRA procedures guide. The nuclear industry is not the only industry that uses PRA, of course. It's a very generic, germane approach to handling your risks. The one thing I like about this figure, it kind of separates what we're doing in three parts. So on the left-hand part here, we call it decision context, at least the NASA guide did. But in our context, it could be our risk-informed applications. Why do we want to do the PRA? It could be we have regulations or licensing requirements or a risk monitor. So we have a lot of reasons on the left why we want to use this technology. that will then move us into the middle part, which is the how. How do we come up with the models? What are the key elements to those parts of the PRA? And so we'll talk about some of these, of course, this morning and then later in the week. Fault tree analysis talks about how our systems fail. Occasionally, we'll have dynamic models. We often will tie thermohydraulics models and core neutronics models into the safety models, into the PRA, so that we capture that essence of what is the plant really going to do in these off-normal scenarios. The little box in the lower, kind of almost right, talking about model parameters. I think that might be an actual rocket engine kind of depiction. That's not your core. But that would be performance related to the components and the people and so on. But eventually, we bring all of this rich, robust information and knowledge and models together to answer questions. And we're going to spend the next 4 days really on the right-hand side of this. What are the insights? What are we going to do with those? How do those relate to licensing, safety, risk-informed, performance-based approaches in the nuclear arena? Coming back to risk just briefly, I mentioned CDF as a surrogate for something else. And that something else is we could look at risk in terms of population. So, for example, we could look at deaths due to cancer, deaths due to accidents. And where we would start then, if we want to kind of have an idea of our risk tolerances and our risk thresholds, is we would simply go out and count, because this is a case where we do have a large population of data, how many cancer deaths are there, and in this situation we're looking just in the US, per year. The number I have there is from 2020. These statistics, of course, lag a couple years. It takes a while to collect those. But that's sort of the risk of just being a member of society in the United States in terms of dying from cancer. It's an oddly specific number. Of course, it has to be an integer, but there's uncertainties on that number, of course. I mean, we don't really know that there was 608,371 people exactly. Record keeping any place is not that good, but nonetheless, if we take that number and divide it by the entire population, which again is an oddly, weirdly specific number, which changes by the second, that gives us kind of an average risk living in the US as a member of the population. And you can express that in a couple of different ways. 1.8 e to the minus 3 cancer deaths per person year. So you're going to see that notation all through the week. 1e minus 4, 1e minus 5 kind of numbers. But that gives you a sense of what those illustrate. That number, though, does represent individuals, does represent you. The thing it does not represent, though, in this case, are individual lifestyles. Do individual lifestyles increase or decrease that number? What do you think? For sure? Sure. It does. And so we could specialize this. But for what we want, if we want to have a sort of a cancer-related or a fatality-related metric, we can start from this to say, well, if I was running an operation that was going to be sort of equivalent to just having the same background level of cancer risks in the US, my facility would produce 1 divided by 550 cancer deaths per year. That gives me a metric, because if I want to say, well, I want to be safer than just kind of the average cancer risk, I want to be something below that, I can take that now and change that. I can say I want to be 10 times safer, 100 times safer, 10,000 times safer. And to set that limit, it really depends, of course, what your facility is producing. If your facility is producing something of great value to society, that tends to say you can elevate your risk because society is getting something for that. If on the other hand, your product is not really valuable to society, which doesn't apply, of course, this week, you would want to have a really low risk tolerance. You'd not want to kill anybody, really, if you're not producing something of value. But those are the kinds of decision trade-offs you get into as regulators, as members of Congress, as owners and operators of facilities. What do I want to do with this, and how do I want to impact the public? So we, as an industry, and specifically the NRC as an agency, can take that kinds of information and produce a variety of tools for us, regulations that will help guide how we operate as an industry. So for example, one of the things that the NRC has done is produce what are called the QHOs, or quantitative health objectives. These have been around for a long time, of course, and back in the day, what was decided was we want to be kind of 1,000 times lower than that background cancer risks when we run our nuclear power plants. That translates into then that 0.1% of the risks. And so if I continue this quantitative dialogue, my risk metric then would be 1,000th of really what was on the previous slide. That then translates into these numbers here, 5E minus 7 for fatalities per year, and then the 2E minus 6 per year for latent fatalities cancers. And again, where that number comes from, if I jump back a slide, take the 2E minus 3 per year, divide that by 1,000, that gives you the 2E minus 6 per year. Simple calculus. Okay. Now you may not like the 1,000, because that, of course, then imposes criteria for you to operate your facility. You might ask, why is it not 100? Somebody else could ask, why is it not 10,000? There's a rich history. If you want to know more about where did we get the 1,000 as an industry, Google that. There's a lot of angst and dialogue, again, back in the 70s and 80s, that eventually came to a consensus on that number. And we live at that number now, but not going to talk about where it came from. Instead, though, as we move forward, we have, of course, as an industry, adopted risk-informed practices. We'll see that greatly expanded on this week. But we have a rich history to really base what we're doing on. We've learned through a lot of little baby steps and maybe some gianter steps. I've, in this slide, highlighted some of the key kind of early stepping stones or stepping points to risk-informed regulation. And you notice this really started in terms of a concept and quantitatively coming up with insights in the 1960s. GE had a siting and design document that used really early elements of PRA. That evolved into something called WASH 1400, the Norm report, Rasmussen report. We'll hear more about that tomorrow. That led to things like the Atwis rule. And of course, behind every one of these boxes are technical reports, white papers, regulatory guides, industry positions, and so on. A lot of technical information to help us understand whatever the concepts or questions are that we're attacking on this slide. And we evolved then the PRA models, the individual plan examination models, or the IPEs in the 90s. The SPAR models, those are the NRC models that they use. So this technology has gotten fairly mature at this point. And that's a good thing, because you'll see this week that we use this technology for an awful lot now. And if it were an immature technology, we would be a little uncomfortable, because we would be kind of on maybe a cutting edge, and we tend not to want to be there. We want to know and have a lot of success in our decision making, and we have that, fortunately. So a little bit of evolution. Professor Golay, who's the co-director of this course, will come in tomorrow, well, actually I think virtually maybe, and talk more about the rich history and get into a little more detail there. I mentioned the WASH 1400 PRA. That was really the first full-blown nuclear power plant specific PRA model. This is available, of course, in PDF online. You see, handwritten graphs and models and typewritten report, of course. But this report was important because it really paved the way for how we really need to think about risks in our nuclear operation, how we need to think about scenarios and models related to those risks, and how we can turn that from an idea into a science, into a rich knowledge base of the facility. So it was the early snapshot of what we've now evolved and call PRA. This was in the 1970s. We didn't know everything. We still don't know everything. There were some weaknesses. These things get reviewed by a large panel, of course. Some early insights into things like common cause failures. We didn't have a good handle on that back in the 70s, I would say. We certainly didn't have a good handle on human reliability, I think, in the 70s. All of that has evolved. The models have evolved, the thinking, the data that we have behind, and we'll talk about some of these elements and see what we have today. Now, a little more complicated picture, similar to the NASA diagram, is this one here. And New Reg 1150 was really one of the bigger activities after WASH 1400. Industry, NRC, kind of a project where they did 5 PRAs on a handful of different plants. Really developed the construct here of all of the elements that go into, let's call it a modern PRA. Initiating events, event tree analysis to handle the scenarios, fault trees to handle the systems. What goes into the systems then are the component parameters, the reliability models, the human, common cause failures, and so on. All of that first box is called level 1 PRA. And what comes out of that first box then is the core damage frequency, CDF. If we continue, which we don't have to, if we want to know more about our facilities, we can go into what's called level 2 analysis. That's where we look at post-core melt, what's going to happen to the core if it starts to melt, what's going to happen to those radionuclides, will they be released to the public, what does that source term look like? Eventually, if we want to keep going, we move into what's called level 3 PRA, which then quantifies the consequences, the dose, the cancers, the monetary impacts, the land contamination, and so on. So potentially a lot of detail here. We don't have time to talk about all the detail. We'll see, again, more of how we apply these technologies this week. Let me talk a little bit, though, about some of the models we have. Event trees, kind of the highest level model that identifies the scenarios. Typically, we have an initiating event that starts each event tree. So you can think of an initiating event as we lose offsite power. That would be an initiating event. Or maybe you have a small break loca. That would be an initiating event. And then how is the plant and the people going to respond to that? That's the wiggly lines in the event tree. And we use that then to quantify, well, really first characterize the scenario evolution and then quantify the outcomes. So here's a simple event tree where we start on the left with the initiator or the initiating event. So imagine we lose offsite power. That's t equals 0 in terms of a kind of imaginary timeline. And then we move from left to right. The accepted practice in this industry is whatever the top event is, failure of that is we would take a down branch. Success of that is we take the up branch. Typically, the first question we ask is related to one of the key fundamental safety functions we have, that is core neutronics. So do we shut the reactor down via RPS, the reactor protection system? And so that first box, instead of saying first top event, would say something like RPS. And then it would be, the up branch would be RPS works, which again, it does 99.99% of the time. But the down branch would be RPS doesn't work. Now you're probably sitting there and say, I've seen a lot of industry experience, never seen an RPS not work. Does that even make sense? And the question, or the answer to that question is yes, it makes sense, because there is a chance RPS will fail. But to get at that probability then, underlying that, we would have the little yellow model called a fault tree, and we'll talk about those in a second. So in other words, we end up with a kind of a hybrid, a combined model. We have fault trees behind all of these branch points in the event tree. Because I need to talk about RPS, or cooling, or auxiliary feed water, or injection, or RICSI, or whatever your plant's going to do following that initiating event. Ultimately, though, I will trace these scenarios to end states. And that's where I would come in with my pencil and say, if I follow this scenario, for example, if everything works, so I take the up branch and stay on sequence 1, that would just say, okay, I wouldn't quantify that at all. Plant did what I expected it to do after I lost offsite power. It's built into the model, but we don't really quantify that. Instead, some of these scenarios would go to core damage. And so I would pencil in core damage for those. And that's where the PRA people then would focus on those scenarios. And we'll spend a lot of time focusing on core damage scenarios this week. The fault tree then, for each of those top events, they will represent systems, structures, components, or functions. So I need to have a corresponding model, a logic model. Fault tree is one that we commonly use. We can have other models, reliability block diagrams, simulation models, and so on. But fault trees are the common approach here. It's a top-down approach, meaning we define, okay, auxiliary feed water fails. That's the top box in the fault tree. And then from there, we say, what are all the things that would cause auxiliary feed water to fail? And from that, we will be able to get then a probability that AFW does not work. Pictorially, what that looks like is something like here. We have the top box that will then be characterized by a logic expression, typically an AND or an OR gate. And then we divide that, or define that next level of, okay, maybe I have 4 pumps in auxiliary feed water. Maybe 3 of those have to fail. So I would have to start to enumerate then the combinations here. Now maybe a pump train has a pump and a valve and a MOV and so on. I would then start to build that detail in lower levels of this logic. And at some point I stop though. I stop at the basic event level. And that's typically where we have reliability data for our components. So a check valve fails to close. A pump fails to continue operating. An MOV doesn't open. So I would have fundamental failure modes at the lowest point in my fault tree. And I capture then the system dynamics, the system behavior, all of the different failure modes in the fault tree. And I have a variety of failure modes. And I have to understand that. If I don't understand my system and how it operates, I can't do a PRA. But that, again, is one of the knowledge base ideas here that we're talking about, ways to capture how this facility is going to operate. So things can fail to start, fail to open, fail to shut down, and so on. I might talk about the mechanisms. I could talk about things like corrosion, fatigue. I tend to go at a higher level, just talk about failures and successes in terms of the fault tree, though. But nonetheless, I want to be as inclusive and comprehensive in that model as I can also. So I will have many systems, structures, and components represented, the hardware part, but I might have controller failures in there. I might have human errors in the fault tree. Could be fails to restore. It could be something's out for test and maintenance. So I will have a variety of conditions, though, that would cause a component not to operate. And again, those will be built into the lowest levels of our fault trees. At that lowest level, then, we have fundamental probability models. We'll talk about what is the probability that that valve does not open. In terms of being able to see the valve, it's either a yes, no, either the valve opens or not. But in terms of the PRA, I need to translate that sort of what do I observe into a probabilistic kind of a question. Probabilities are not observable, but nonetheless, we use what we see, failure successes, to infer the probabilities of things failing. So in a simple example here, something failing to run. I'm worried about a component, maybe a pump, not functioning for 24 hours after an initiating event. That translates into a probability question. What is the probability that that pump will not operate for 24 hours? And so to answer that, I need a couple of things. I need to know how long I'm asking for that pump to run, 24 hours. And then in this case, I would need something called a failure rate. How likely it is for that pump to fail over time, over that 24-hour duration. I put all of that together, put it into what's called, in this case, a Poisson model. That will give me the probability that that pump fails to run. And that's the kind of concepts then that would be at that lowest level in the fault tree model. Now, when we get into the fault trees and the basic events and the component failure probabilities, we bring in science to help us answer these tough questions. So things like probability theory, probabilities, the data analysis that go behind that, is all key to being able to successfully quantify a PRA. So just some of the concepts that we see in that world, ideas like independence, that just translates into a mathematical expression. If I assume something fails independently, that gives me a way to write down a probability expression and quantify that. Now, the problem is that's an assumption. I can assume everything fails independently, but what we know from real-world examples is sometimes we have dependent failures, common cause failures, that then introduces a complexity in our probabilistic model. But nonetheless, we have starting points, things like independence, dependence. These are concepts that have been around for hundreds of years, and the probability theory that we're building on has been around for hundreds of years. In the art industry, we have then a couple of workhorse models that we use in the PRA. Again, not too important to know all the gory details here, but I'm just lifting a little bit of the curtain to show you what's behind the black box that we call PRA. But two of the important models that we use, a Poisson model that represents occurrences in time. It's a probabilistic model. And then a Bernoulli process that represents kind of start-stop, flipping a coin, demand-related failures. Those two models probably represent, if you have a PRA at your facility, it probably represent 95% of the math behind the basic events in your PRA model. Now, you may have walked in here today not knowing you had a PRA, not knowing you had a Poisson and Bernoulli process, but now you do, so you can check that box off for the day. But again, what these are just the probabilistic expressions and the math that goes behind the PRA model. I mentioned in the fault tree itself then, we have what's called Boolean algebra, logic models. If you're any, excuse me, electrical engineers or computer scientists in the room, any double E's, a couple double E's, you probably know this better than I do. Truth tables, logic, lookups, set point trips, how you design RPS, and in OR gates. That is also a pervasive technology in the PRA because all of our event trees and our fault trees get translated into Boolean algebra. Your PRA gets translated really into one very long string of equations that's Boolean algebra, a bunch of and OR gates. And so to formally quantify those, we have expressions. So for example, if you have an OR gate, kind of the approximation is if you have A and B, or excuse me, A or B, you just add up those probabilities, PA plus PB, that's an approximation. If they're mutually exclusive, which things are usually not. We have to subtract that little intersection of the two events on the Venn diagram. Again, details. But just think, an OR gate, you add probabilities, as opposed to an AND gate where you multiply probabilities. So if I take those two same events, A and B, and say they're in an AND gate now, the probability coming out of that gate is A times B. So you're going to kind of lower the probability in that case rather than increase it with an OR gate. And that makes sense. If you say I have two safety systems that they both have to fail, first one has to fail and the second one has to fail, that's good. If I say either one, if it fails, I'm in trouble, first one or the second one, that's going to be a higher probability. And that's why we have redundancy in our facilities, really because of this kind of a concept. We want to lower the probability that a safety system will fail. And then lastly, we want to quantify all of the probabilities in the PRA. We have to do that if we're going to quantify that. We, over time, have become Bayesian. Again, you may not have known that walking in the room. If you use a PRA in your facility, you are a Bayesian. What that means is just a formal approach to quantifying the probabilities. The nice thing about the Bayesian approach, it combines engineering knowledge with statistical information. So we take the data that we collect, the operational data, we'll hear more about that this week, combine that with our engineering knowledge about components and systems, and quantify a probability, including its uncertainty. A very powerful approach to encoding information related to probabilities. Another important concept to take away is the distinction between frequencies of events and probabilities of events. We started with core damage frequency as a metric. That is, how many core damage events do I get per year at my facility? Now that's a small number, of course, 10 to the minus 5-ish, maybe 10 to the minus 6. But that's a frequency, that many events per year. I used to work at the Idaho National Laboratory before I retired and became a professor. I remember doing a PRA for the Advanced Test Reactor at INL in Idaho. And they had, so it's a test facility, and they were moving 40-ton casks, but they would do that 120, 150 times a year over the reactor while it was operating. So that would be a case where the frequency of something is 150 per year, but then you could talk about what's the probability of dropping a cask. And you put those together to find your risk of dropping a cask. So you need to know the frequency part, how many locas you have, how many loss of offsite powers you have per year, how many cask movements per year. But then you translate some of that into what's the probability of the core melting, given you have a loca, given you have, and so on. Two different but kind of related ideas, frequencies versus probabilities. Mentioned initiating events. So in our industry, we have a long list of potential initiating events. 40, 50 potential things could cause that upset condition. We, of course, group those in or characterize those into different groups. Things like internal events, kind of internal to the facility. Those are the ones you're probably most familiar with. Locas, transients, and so on. We also have to worry about external events, as they're so-called. Earthquakes, fires, external floods, and whatnot. But they're all just initiating events. They all have their own event frequency. Excuse me, and then they would have their own event tree. But again, those are scenarios. That first domino, that's the initiating event. And then as we progress, we use that event tree model that we showed to tell you what's going on in a particular scenario, but then also produce the combinations of things that might fail to get us to a core damage state. Again, and just a refresher here, success, up, failure is a down branch. This is a little more specific to a nuclear example where we have a generic initiating event, but then RPS would either work or not, emergency coolant, and it could be a system or a pump works or not, the second pump works or not, and then we might have DHR for decay heat removal. Depending on the scenario, there are different frequencies and probabilities of going through each of these scenarios. And what comes out of this then is the core damage frequency, and specifically all of the combinations that get me to core damage. And those combinations are called minimal cut sets. The minimal cut sets are the initiating event and the pump 1 fails, the check valve 2 fails, the human doesn't restore. That would be an example of a cut set. Just the specific combinations of things that fail that lead to a core damage sequence. Now you can imagine there might be a lot of ways to get to core damage because there are a lot of components, a lot of things that could go left or right, up or down, true or false, work or not. But the PRA has been designed to capture all of the combinations that would potentially lead to core damage. Okay. A little bit of the history of fault trees before we leave this topic. Fault trees actually predate PRA. It's a technology that kind of started maturing in the 40s and 50s, but then with the military and specifically projects such as the Intercontinental Ballistic Missile Program, the folks who are working for the military wanted to know how reliable those systems were. And so they invented things like reliability block diagram approaches, fault tree approaches, to quantify how robust these systems are. Where can they change the system to make them more robust? Obviously, these are high-value systems. We don't want them to fail. We want them to be reliable. Took some text out of a apparently 68 Los Angeles Times classified ad looking for folks to do safety reliability analysis. Again, the technology has evolved. I mentioned INL already. A lot of the tools and technologies we actually use in the nuclear industry came out of INL. A lot of the nuclear reactor testing came out of INL. Spent 33 years there. I'm a little proud of that place, so I might mention it more than once, but nonetheless. One of the things that INL has done over the last 50 plus years is work on computational methods for things like thermal hydraulics, neutronics, but also PRA and reliability. And this idea then is we're working from the scenario concept at a high level. We work down, we have scenarios, we then have fault tree system models, ultimately basic events that represent components. We bring all of that together. Again, that's what's called a PRA. And the job then of a fault tree analyst would be to look at the system and figure out the ways it fails, and then transcribe that into a fault tree. And the illustration here then shows, okay, I have a piping and instrumentation diagram on the left there, where I have some kind of, let's assume it's water going into a valve maybe, and component B and C might be pumps. And I might have a check valve on the right-hand side called component D. But I need to worry about the failure modes of that. So I look at the system and then figure out the failure modes, the and OR gates, and ultimately then produce that fault tree on the right. That's what a fault tree analyst or a reliability engineer does. That translation called FTA. In terms of the symbols we use in the industry, circles are basic events. Those are the lowest levels in the models. Those are where the components and the human failures are. But above that then would be all the logic gates, the and OR gates. We have some special gates such as N out of M. If you have 3 out of 4 have to fail, you would use an N out of M. That way the computer can just figure out all the combinations rather than you having to figure out all the combinations. Little triangle is a transfer saying this logic is duplicated in other parts of my PRA. So over time, we've come up with, of course, tools and methods for the madness. And then in terms of how we actually do reliability analysis, there's a couple of ways. We tend to focus first on statistical modeling, Bayesian analysis. We'll grab operational data, put a Poisson or binomial Bernoulli model together. The other approach that's not used as much in our industry is physics-based sort of load capacity models. For example, if you go into aviation, aerospace, you tend to see more physics-based failure models, maybe because they don't those systems either tend to be a large number of data points where you can do that kind of model, or they're always, we're going to invent the next spacecraft, so always one off, and so you don't have statistics to help kind of back it up. But nonetheless, we have a couple of ways to do reliability analysis. We use statistical modeling. We collect industry data. We then quantify our probability models using a Bayesian approach. Those, again, have to be tied to the operation of the components. Is this a demand kind of a component where I want it to open? Is it something time-based where the component has to keep operating for some sort of fixed period of time? And depending on what kind of component it is in failure mode, then we select the probabilistic model. Yeah. And essentially, a reliability engineer then is going to come up with this picture on the right here, where the red curve is the reliability of the component or the system, whatever it represents, a time to failure. And you can imagine then that red curve is what's embedded in your PRA models when you have something that says the pump fails to run, or the flex system doesn't function for 24 hours, or the diesel doesn't work for 12 hours. It's really that red curve that's behind that statement in the PRA model. And again, we have formal reliability methods, the math behind that, all of the probabilistic concepts help us quantify. And then we want to be very thorough and systematic when we come up with a risk or reliability model. And so we typically will define our plant in terms of a structure like this. I call it a failure event classification. You can call it kind of almost a hierarchy of your components and systems and how they might fail. Starting at the system level, you could have a system, AFW, auxiliary feed water. But then you have, of course, multiple components in that system. You would have to then define what those are, talk about the failure modes for those components, what is or is not affected when something fails, what's the mechanism, and ultimately what are the failure causes. Just a way to decompose the system that you have in front of you. And remember, our PRA is a knowledge base, a very rich knowledge base. So you're encapsulating really all of the structure of your systems and all of the scenarios, the operating procedures, the thermal hydraulics, the neutronics. You're embedding all of that behind the scenes in the PRA model. So we have a couple more slides here. We're going to finish up a little early to give you a chance to get some coffee and a donut. I don't know if we have any Boston creams over there, but one of the favorite pastries in town. If this is your first time in Boston, please grab at some point a Boston cream. And if you really want the full experience, find the closest Dunkin' Donuts and get a Boston cream. But I'm deviating a little bit. So a couple of special topics now. One of the failure modes we have to worry about is CCF, common cause failures. We worry about that because it defeats redundancy. So we spent 70 years figuring out how to make these systems safe and reliable. And then on Monday morning, you're telling me we have something that kills all the redundancy I just built into my system. Like, what is going on? But the reality is, sometimes we hear weird things going on. Sometimes we will see multiple components failing and doing from the same cause. And if we look at the data related to that and the predictions related to that process, it would not be copacetic to assume our components fell independently. If we assume things fell independently, what we're going to ultimately do is underestimate the failure probability. We'll be non-conservative. And as you probably well know, the word non-conservative in the nuclear industry is not a great word to be associated with. So we could assume everything fails dependently. You could assume that 100%. That would be a horrible assumption. But that's kind of the other spectrum side of that coin. So instead of that, we say, well, is there something in between? Is there a specific dependent failure model that we could bring to the table? And again, over time, we figured this out where we can have somewhat robust common cause failure models. we can take what limited operational data we do see related to CCF and quantify those models. And then, of course, we would build this into the PRA model. And so this is a sort of a special part of the PRA model, specifically addressing the dependence and the failures thereof in our nuclear power plants. The reasons why we might have dependence, list just some of those here. The NRC has recently gone through a fairly large project looking at causal CCF. What are the underlying causes of CCF? These are the kinds of things you would see in that kind of a project. And we'll hear more from the NRC later this week, of course. I mentioned then we quantify our basic events. We do that through a Bayesian process. We use operational industry data. We have a lot of data at our disposal, fortunately, for things like failure rates and failure probabilities. Now, we don't have an infinite supply. We don't have data such as the insurance industry does, but nonetheless, we as an industry and NRC, IMPO, you all help us collect this information. So as an industry, we get better together, actually. What that looks like, it translates into documents over time. Some of the past PRAs, I mentioned New Reg 1150, WASH 1400, were really early collections of operational data. Other industries, IEEE has standards related to failure rates, failure probabilities, but what we have are predominantly industry-gathered NRC process data. Those get published typically as a new reg, and you can see the years there. Those data files get updated over time because we really want to represent kind of what's going on at my facility, what's going on in industry. Industry practices change over time, so having failure rates from 60 years ago probably would not really be mostly applicable today. The most current data that we have is embodied in New Reg CR 6928. The last update was in 22. They're processing an update now, so about every 5 years they update that report, so we can again use kind of current cutting edge data related to what's to be found in the PRA model. Another special model that we put into our risk assessment is related to human actions. Specifically, we call that HRA, a human reliability analysis. It's looking at how folks in our facilities could either hurt or help, and translating human actions into quantitative probabilities. Just briefly, that tends to follow something like this process here when you're doing a HRA. Find out, what are the sources of those human errors, what might happen related to the actions thereof. We end up then putting these into a quantitative model. So first of all, look at the tasks, what's going on related to that, kind of almost like a failure modes and effects analysis, but for people. Model those. There's different models for HRA, just like there's different models for PRA. Sequence kinds of models, stepping through time tend to be a good model. But then ultimately we'll want to quantify the human actions, whether they be, fails to recover, could be a human action. We want a pump to be restored after it trips offline. What's the probability that the operators will not do that in time? That would then be translated into a probability that goes directly into the PRA fault tree. So, in summary, that was a quick whirlwind tour of some of the technology and elements that you find in a PRA model. And again, we're going to spend the week talking about some of these elements in full sort of exposed view. We will definitely be talking about the applications of these models. One of the key takeaway points, though, is that last bullet. This is a way to represent your facility kind of in a digital version of what we expect to see in reality. So that knowledge repository is a way of kind of explaining what is a PRA. If you don't know your systems, if you don't know the key elements, thermal hydraulics, neutronics, and so on of your system, if you don't have procedures related to your systems, it's hard to come up with a PRA. because you have to encapsulate what you expect to see in these models. Yes, there's a lot of theory. Yes, there's a lot of math behind that. Yes, there's a lot of geeky kind of looking guys and girls who put these things together. If you want to know more, I teach a PRA course here in the spring. Come back, we'll run you through that. But at that point, I'll just stop and ask, are there any questions related to PRA, or I'll look ahead of what's coming down the road? So thank you. Questions?